Welcome to Maths with EJD. In the previous video, we talked about Taylor's and Maclaurin series, and we can see that with those series, we can actually, get polynomial-like expressions for any kind of function, like transcendental functions, including trigonometric functions, hyperbolic functions, and all of that. So this video is actually meant to highlight how some of these power series for different functions look like. So let's go. First of all, as a way of reminder, we know that a power series is an infinite sum, of the form f of x equals summation from n equals 0 to infinity of an x minus c raised to power n. So this is what a typical power series looks like. Okay, of course, we remember again that an are the coefficient, they are coefficients. C is the center, of the series, and x is the variable. Okay. Of course, power series are invaluable in expressing functions as infinite sums. Which can be truncated to approximate functions, with a desired level of accuracy. So if you want to approximate a transcendental function like the ones I've mentioned, you just need a power series for it. Of course, since it is an infinite sum, so if the level of accuracy you desire will determine how far you go. So if you go 4 steps, the accuracy you get will not be as high as when you go 10 steps, for instance. So that's the idea of power series. So let's talk about some examples of power series. You already know some, at least coming from Taylor series and all that. So let's see some examples of power series. So first of all, let's talk about the exponential function. That's e raised to power x. Okay. Of course, you already know how to derive it. You just say f of x equals e raised to power x, and you keep differentiating. Interestingly, for exponential function, it's like the cat with infinite lives. It never dies. E raised to power x is retained no matter how many steps you go. Of course, the coefficients and all of that will change. And of course, the center will also determine based on whether you're using Taylor series or Maclaurin series. So generally, e raised to power x is equal to the summation from n equals 0 to infinity of x raised to power n all over n factorial. That's the general form. And of course, that means that it is the same thing as 1 plus x. Of course, you can even expand this. Just follow starting from n equals 0. So 1 plus x over 1 factorial plus x squared over 2 factorial. Technically, this is like that one is actually like x raised to power 0 over 0 factorial, because x raised to power 0 is 1 and 0 factorial is also 1. So that's what it's like. So plus x3, x raised to power 3 factorial, and so on and so forth. So that is what exponential function looks like. So if you want to take an example around this, then we'll have we can do something like this. Okay, let me use the same marker. So if you take an example and say approximating e when that's, of course, e means when x is equal to 1. E raised power x is general. So, but when x is equal to 1, you have e raised power 1, which is simply e. So, approximating e, that is when x is equal to 1, with the first four terms. With the first four terms gives, in fact, I should talk about binomial expansion very soon. This terms thing is making me remember that. So e raised power 1 with the first four terms of that expansion would be, 1 plus 1 over 1 factorial, So we are taking these four terms actually. So we have 1 plus 1 over 1 factorial plus 1 squared over 2 factorial plus 1 cube over 3 factorial. So these are the terms we are taking. So that means e raised by 1 is approximately 1 plus 1 over 1 factorial is 1 plus 1 squared is 1. 2 factorial is 2 times 1, which is 2. 1 cube is 1. 3 factorial is 3 times 2 times 1, which is 6. Okay. So if you sum all of that up, you get this to be approximately 2.6667. Of course, we want to confirm that with decimals, as we are always want to do. So you have decimals e raised power 1. Oh, okay, it's like, okay, well, now the actual e raised power 1 is 2.718, right? But if you, because you can see it's a bit not it's 2 point something, right? But it's not exactly this. So what we have done is 1 plus 1 over 1, of course, 1 over 1 plus 1 over 2 plus 1 over 1 divided by 3 factorial, which is 6. See what you get, 2.66. So you can see how far it is from that. If you want more accuracy, for instance, if you add the next term, which is 1 over 4 factorial, that's 1 over 24. Okay, so you can see it's getting closer. In fact, the next one is 5 factorial, which is 24 times 5, that's 60. That's 1 plus 1 over 60. So you can see it's getting closer and closer. So depending on what exactly you want. 4 factorial is 24. 5 factorial, that's 5 times 24. 240. Oh, that's 1 over 120, actually. 1 over 120. Yeah, it's yeah. So you can see it's even closer. So the accuracy you want, the number of times you have, the better the accuracy. That's exactly what it's about. So if you want higher accuracy, you go more times. So this is that for exponential function. So let's move on to the next one, which is 2. Sine function, which is sine x. Sine x. So of course, I think, I'm not sure, we did this in the last video, but of course I'm just stating the power series here. So sine x is simply x being an odd function. You can see it's always the odd powers. So x raised power 1 minus x raised power 1 over 1 factorial minus x raised power 3 over 3 factorial. So the signs are also alternating. So that's why sometimes they call them alternating power series or something. So you have x minus x cubed over 3 factorial plus x raised power 5 over 5 factorial minus x raised power 7 over 7 factorial. Of course, if you want to continue that way, plus x raised power 9 over 9 factorial minus x raised to power 11 over 11 factorial. But I'll stop here. Okay, so this is what sine function looks like. So, and if you want to take an example under this, that will be maybe let's approximate sine 30 degrees. Pi over 6 is 30 degrees, by the way. So approximate sine 30 degrees. Of course, here now, since pi over 6 is in radians, so if we talk about radians, so we have pi over 6 to be approximately 0.5236, like that. So if we do this with 3 terms, So it means that we're going to get, so it means we'll get sine pi over 6 to be approximately, so if pi over 6 is 0.5236, so it means x now is 0.5236 plus the next one. Okay, actually it's minus. So we have minus 0.5236 raised to power 3 all over 3 factorial, of course, is 6. You know, we are using 3 terms. Then we go to, if we use, okay, okay, let's use 2 terms. Let's use 2 terms. So we have, let's use 2 terms. Okay, let's use 2 terms. So we have these 2 terms, and the answer is approximately 0.4997. Of course, that's really close to, okay, that's 0.4997. And we know that sine 30 degrees is actually 0.5, right? So, but if you want more terms, you can keep going. So let's see from decimals what we get. So let's say that sine pi over 6. So we have sine pi divided by 6. Okay, that's 0.5. But if we use, in fact, we can even substitute the pi over 6 directly, right? So we know we have pi divided by, okay, I mean just pi, right? Pi minus pi divided by 6 raised to power 3. So you can say that's 2 points. In fact, like it's a fact, right? But of course, you know, we used I guess something is not right here. Okay, I mean this doesn't work. So we have to use that 0.5236 actually, because normally pi divided by 6 is 0.5236. So it's better we use that, because if it is not in trig, pi will come as 22 over 7. So we have 0.5236 minus 0.5236 raised to power 3, all divided by 6. And we have that 0.499, blah, blah. So if you want better accuracy, you can go the next step. That's plus 0.5236 raised to power 5 divided by 5 factorial, which is 120. So you can see this literally 0.5000. So it's really, really close. So the more times you have, the better the results you get. That's the point. Okay, so that's for sine function. Let's talk about the next one now. Let's talk about the cos function, the cosine function. Cosine function, which is cos x. So cos x is an even function. So you're going to have the powers of x starting from 0 then to 2. So because it's even, so even function. So we have cos x to be x raised to power 0 over 0 factorial, which is simply 1, you know, minus x squared over 2 factorial plus x raised to power 4 over 4 factorial minus x raised to power 6. It's also alternating over 6 factorial, and so on and so forth. Of course, if you want to go on, that'll be plus x raised to power 6 over, I mean, x raised to power 8 over 8 factorial minus x raised to power 10 over 10 factorial and all that. So that if we take an example to approximate cos pi over 3, I mean cos pi over 3. Pi is 180, so pi over 3 is 60. So of course, you from trig, I mean, if you check the trig playlist, you discover that the sine of an angle is equal to the cosine of 90 minus that angle. So it means that sine 30 is the same thing as cos 90 minus 30, which is 60. So you expect cos pi over 3 to also be 0.5 normally. Okay. So in this case, approximate cos pi over 3, cos pi over 3 with three terms. So if we do this with three terms, see, we have cos pi over 3. Of course, because pi over 3 actually is 1.1.0. Of course, pi is something like 3.142 or so. So pi over 3 is actually 1.0472. So if you take that value, right, because pi over 6 would be approximately, of course, the first one is 1 minus 1.0472 raised to power 2 divided by 2 factorial. That's basically 2 plus, of course, this is minus. So the next one is 1.0472 raised to power 4 divided by 4 factorial. 4 factorial is 24. And the answer is approximately 0.7382. So it's a far cry from the 0.5 that this should actually be. But the number of terms, as the number of terms increase, you get better results. So let's check Desmos for this. Of course, we know that sine pi over 3 is 0.5. Sine, we are dealing with cos now. Cos pi over 3, pi divided by 3 is 0.5. But then, if of course, pi over 3 itself is 1.0472, like we saw already. So if you do the next one, so we have 1 minus 1.0472 raised to power 2 divided by 2 itself plus 1.0472 raised to power 4 divided by 4 factorial, which is 24. So we are taking these three terms. Okay, I mean, what we have previously is not accurate. Let me change that. So this is actually, okay, what's that again? This is 0.5018. Let's do it that way. 0.5018. So 0.5018. But of course, the actual result is 0.5. So it's a far cry. But if you go a step further, you see you get closer to that result. So now you have minus 1.0472 raised to power 6, being an even function, divided by 6 factorial. 6 factorial, I think, is okay. Let me just put 6 factorial directly. 6 factorial. So you see, it's even closer now. You have 0.49999. So I'm sure by the time you add the next one, it will go. You get the. I mean, if you get something almost like 0.5. So you have 1.0472 raised to power 8 divided by 8 factorial. Oh, okay, it's still getting closer. So I think I want to stop there and move on to the next thing. So that is about cosine function. So can we take log function now? Question number 4, we have logarithmic function. Say we take ln 1 plus x, for instance. Let's see what that gives us. So ln 1 plus x. Of course, normally, right, if you're going to do the whole, okay, maybe I should even do this. Should I? Okay, let me do this since we've not done it before. So here, you have f of x. Let's take it that we are expanding it. We are doing the Taylor series for the Maclaurin series, actually. So f of x is ln 1 plus x, right? So that f prime of x is equal to, of course, straight up, it means that f of 0 is actually ln, because x is 0 now, so that'll be ln 1, and ln 1 is 0. The log of 1 to any base is actually 0, because 0, anything raised power 0 is 1. So that's the connection. So f prime of x here, to differentiate a logarithmic function, right? Differentiate the inside the bracket. So differentiate 1, that's 0. Differentiate x, you have 1, divided by the original thing, 1 plus x. And that implies that f prime of 0 is actually 1 over 1 plus 0. And that's simply 1 over 1. And the result is, okay, now I'm talking about ln. okay, it's lim you're dealing with, right? So that will be okay. Now the function has changed, so no longer lim, sorry. So just put 0 here. So you have 1 over 1 plus 0, and that is 1 over 1, and the result is 1. So that's the next term. Then of course, you already know for Taylor series, right? That f of x is usually f of 0 plus f prime of 0, plus f prime of 0 x, f prime of 0 x plus f prime prime of 0 x squared all over 2 factorial, then plus f prime 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 of 0 x cubed all over 3 factorial, and so on and so forth. So that's what Taylor series looks like. So you have this. So, of course, it is infinite, like we know. So, okay. So this is just me trying to derive the expression. So, of course, if we go next, it means that, of course, this is the same thing as 1 plus x raised to power minus 1 now. So it's easier for me to differentiate this way. So if we go f prime prime of x, that will be differentiating this. So, and to differentiate this, right, this is function of a function. And the 3 easy steps: bring down the power minus 1, differentiate inside, that is 1. Then the original thing you had as 1 plus x, reduce the power by 1, that's minus 1 minus 1, that's minus 2. So we have minus 1 over 1 plus x all squared. So it means that if we do f prime prime of 0, we simply have minus 1 over 1 squared. So this is simply minus 1, right? And then so that means we have minus 1 plus x raised by minus 2, like that. So we can go to the third one, f prime prime of x, and that is minus is there already. That's like minus already. Then bring down the minus 2, that's minus 2 times 1 plus x. Reduce the power by 1, that's minus 2 minus 1, which is minus 3. And then you have minus and minus is plus. So you have 2 over 1 plus x raised to power 3. So that implies that f prime 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 of 0 is actually 2 over 1 cube. So that's simply 2. So you can substitute this into the, okay, well, I can rewrite that. So we know normally f of x should be f of 0. Did you even do f of 0? Yeah, we did f of 0. That's lane 1, which is 0. Okay. So f of 0 plus f prime of 0 x plus f prime prime of 0 x squared over 2 factorial plus f 1 prime prime, that's third derivative, evaluated at 0 x cubed divided by 3 factorial, and all of that like that. So that f of x now is f of 0. Evaluating that function at 0, you get 0. F of 0 is 0 plus f prime of 0. F prime of 0 is 1. Okay, that's 1, of course, multiplied by x plus f prime prime of 0. F prime prime of 0 is minus 1, like we have here. So f prime prime of 0 is minus 1, and x squared all over 2 factorial. F prime 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 of 0, that's what we did last, which is 2. So we have 2 over 3 factorial x cubed and all that. And that is why the expression, for logarithmic function ln 1 plus x is what it is. So we have, okay, let's tidy this up. So this goes, of course, this is x minus x squared, 2 factorial, this is 2 factorial, and that is 2 plus 2 over 6 times 2 over 6 times x cubed, 2x cubed over 6. Okay, I think I want to go a step further. Let's just do this additionally so that we can have more points. So, of course, this is the same thing as 2 into 1 plus x raised by minus 3. So the fourth derivative of x now would simply be 2 times minus 3 into, of differentiating side, that's times 1 into 1 plus x raised by minus 4. So you simply have minus 6 over 1 plus x raised by 4. So FIV of 0 is simply the same thing as, minus 6, simply minus 6, right? Because 1 plus 0 is 1, raised by 4 is still 1. So that the fourth one is minus 6. So of course, this one can go as far as f. Sorry, everything is just getting messed up. So fiv of 0 over 4 factorial x raised by 4, and everything goes on from there. So that means we have so fiv of 0, you have already seen that it is minus 6. So we have minus 6 over 4 factorial, then x raised by 4 plus the rest. So from that, we can get more points. Plus and minus is minus. So we have 6 over 4 factorial is 24, x raised by 4 plus all the rest. So that f of x here is f of x, of course, which is the same as e raised by x here, is all this. So we have x minus x squared over 2. 2 here is 1, 2 here is 3. So that's plus x cubed over 3. 6 here is 1, 6 here is 4. So we have minus x raised by 4 over 4 plus all the rest. And that is why for that logarithmic function, right? So we can say therefore ln 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus x raised by 4 over 4, and so on and so forth. Okay. Of course, you can see the pattern already. We can even go on. So x 1 raised by 1 over 1 factorial minus x raised by 2 over 2 factorial plus x raised by 3 over 3 factorial minus x raised by 4 over 4 factorial plus x raised by 5 over 5 factorial minus x raised by 6 over 6 factorial. So you can see the pattern already. The pattern has formed, so you can just follow it through. But one condition is that there's a condition on x. So for x must lie between minus 1 and 1. Okay. That's really necessary because, log, right? Yeah, you can only calculate log of positive number. So if x is, if x does not lie between 1 and 1, for instance, if x is minus 1, you are going to have log 0. Okay. And if x is 1, you're going to have ln 2. Well, I don't know why that is though. So, but the absolute value of x has to be less than 1, basically. Okay, so if we want to work around this, we can take a quick example, which is this. Using the first 3 terms to approximate ln 1 plus 0.5. Now our x is 0.5. So we simply have ln 1. That's ln 1.5 in short, which is ln 1 plus 0.5. So that will simply be, 0.5 is your x now. So that means you have x. So you have x, which is approximately 0.5 now. Then minus, the next one is x squared. That is 0.5 squared all over 2. Okay, we are using only the 3 terms. Then plus 0.5 cube all over 3. And that is approximately 0.4167, which we can confirm from Desmos. So let's see the exact value of ln 1.5 and see the approximated one like that. So from Desmos now, we see that ln 1.5 is a certain value, ln 1.5. Okay, that is 0.4055. That is that's still approximated in a way, but it is even more approximated when you use power series. So now so ln 1.5 is basically ln 1 plus 0.5. So in this case now, we have 0.5 minus 0.5 squared divided by 2, then plus 0.5 raised to power 3 divided by 3. So you can see it's getting closer. This is 0.41. What we got there was 0.4167. Yeah, this is what we got. If you want it to be more accurate, you go next. Minus 0.5 raised to power 4 divided by 4. So you can see it's getting closer. And so you can keep going actually. So that is about logarithmic function. So, and that was me revisiting Maclaurin series to drive the point home. Okay. So let's go for the fifth one. I believe the logarithm is the fourth one actually. Yeah, logarithm is the fourth one. Let's go for the fifth one, which is this. The fifth one is the arctangent function. Arctangent function, which is arctan x. And I like to write it as this. I feel it's more fanciful this way. I don't know why. So that's arctan x. So let's see what the series for arctan x looks like. Okay, well, I won't go into differentiating and all that because to be really it will be a tough call actually. But let's just go straight and state what it is. So arctan x is actually x minus x cubed over 3 plus x raised to power 5 over 5 minus x raised to power 7 over 7. So it's giving some odd behavior, as we see with odd functions. For log, right, you see that there's an alternation between odd and even together. It's a combination of both odd and even, but then the signs are alternating. But here, this is giving a typical behavior of an odd function, sort of. Okay, so that yeah, it's given that kind of behavior, but then there's a condition that the absolute value of x has to be less than or equal to 1. So the value of x it only takes values from -1 to 1. I think we saw that under hyperbolic. Oh, this is not hyperbolic now. Okay. So we saw something similar to this under hyperbolic functions. So maybe that's a kind of behavior right there. So let's see an example where we try to approximating arctan 1. Of course, arctan 1 is, tan 45 is equal to 1. So arctan 1 has got to be 45 degrees, which is pi over 4. Normally, that's what it should be. And of course, pi over 4 is like 3.14 something over 4. That's 0 point something. So let's see. So approximating arctan 1, which we expect to be approximating arctan 1, which actually which equals which equals um which equals pi over 4. Arctan 1 is actually pi over 4 because tan 45 degrees is 1. Pi over 4 is actually 45. So that's what that's what it should really be. But let's see if we approximate it using all the terms we have here now. So it means we have arctan 1 to be approximately 1 minus 1 over 3. Of course, that's 1 cube over 3 plus 1 raised to power 5 over 5 minus. Okay, yeah, the difference here is, for sine and cosine, for sine that is odd, so all these things are 3 factorial, 5 factorial, 7 factorial, but this one is not factorial, it's just 3, 5, 7, and all that. Then minus 1 raised to power 7 all over 7. By now, you already know that 1 raised to power anything is 1. 1 raised to power 1 billion is 1, So that's why all of these are just 1 straight. So if we do this approximately, it is 0.7. And the exact value is pi over 4, which is roughly 0.7854. So let's go to decimals to see what happens with that. Arctan of 1. So normally arctan of 1 is 0.7853, which is, of course, that's like pi divided by 4. That's what, pi divided by 4 you can see the value is exact. So if we use approximation now, we are saying this is 1 minus 1 divided by 3 plus, of course, 1 raised to power 3 is 1. So I'm taking that for granted that we know that. Then 1 divided by 5, then minus 1 divided by 7. So you can see this is 0.7238, 0.7238. So it's a bit close, but maybe not quite. So we can go minus plus is the next thing, plus 1 over 9. So, okay, I think it's closer than, say, minus 1 divided by 11, and it keeps going like that. So you keep going. The more times you have, the closer it gets to the result. Okay, so that's about arctangent function. So can we talk about the geometric series? I think I made mention of this previously. So let's talk about the geometric series. That's the number 6 now. Geometric series. So for geometric series, that's like 1 over 1 minus x. So I made a connection between the geometric series, yeah, and sum to infinity, and that is what led to 1 over 1 minus x. So in this case, right, this is, you have 1 over 1 minus x. That's the same thing as 1 minus x raised to power minus 1. Interestingly, I've not taught binomial expansion, but if you use binomial expansion for this, right? Okay, maybe I can make a quick reference to binomial expansion here. So so for binomial expansion, right, this is an aside, So if you have a plus b raised to power n, so we have so the first thing, you can have a raised to power n all over 0 factorial plus n. So this n comes down now. So you have a raised to power n, b raised to power 0 actually. Then the next you have n, then a raised to power n minus 1, b raised to power 1 all over 1 factorial plus n into n minus 1, then a raised to power n minus 2, b raised to power 2 over 2 factorial. And that keeps going like that. So the next term, of course, is going to be plus n into n minus 1. And this n minus 2 up here joins it, n minus 2. That's the pattern. And then you have a raised to power n minus 3, b raised to power 3, all over 3 factorial, and so on and so forth. So that's how we get this one. This is general. Yeah, this is power series still, technically, right? So if you're going to apply this to 1 minus x raised to power minus 1, so we have 1 over 1 minus x, right? Which is 1 minus x raised to power minus 1. So following this pattern I just generated now, so our a is 1, our b is minus x, okay? So we have so a, which is 1 raised to power minus 1, that's our n in this case. So n is minus 1 here. So we have a raised to power minus 1, that's 1 raised to power minus 1. Then b is minus x raised to power 0, all of this over 0 factorial. Then plus our n is minus 1, so we have minus 1 into 1. Then minus 1, this is n minus 1, so this will be minus 1 minus 1, that's minus 2. Then now you have minus x raised to power 1 all over 1 factorial. Then next you have, so minus 1 now, then the minus 2 joins it, so we have minus 2, then 1 raised to power minus 2 minus 1, that's minus 3, then minus x raised to power 2 all over 2 factorial. So you see the power of the first one is reducing, whereas the power of the second one starts from 0 and it is increasing. So I can also do the fourth one, which is minus 1, minus 2, minus 3. This minus 3 comes down. So you have 1 raised to power minus 4, then minus x raised to power 3 all over 3 factorial. So I'm going to do a playlist on binomial expansion very soon. I think I haven't done that. So, and it's really very useful. Okay, so now we just need to tidy this up. So we have 1 over 1 minus x to be equal to 1 raised to power anything. This is 1. Anything raised to power 0 is also 1. 0 factorial is 1. So everything in here is 1. So we have 1 there. Then plus, of course, anything raised to power 1. 1 raised to power anything rather is 1. So we can cross out all those knowing that they are 1 already. So here we have minus 1 minus x. 1 factorial is also 1. Then plus minus 1 minus 2 minus x squared all over 2 factorial. Then lastly, we have plus minus 1 minus 2 minus 3, then minus x raised to power 3 all over 3 factorial, and that continues. It's a power series, mind you, so it's an infinite sum. So we're only going 4 terms. So 1 over 1 minus x, so you have 1 minus and minus is plus x there, then 2 factorial is 2. Okay, so we have minus and minus, that is plus. then minus x squared. That will also be plus x squared up there, right? So we have plus x squared. Then here we have 3 factorial is 3 times 2 times 1. So that cancels 3 and 2. So we have minus, minus, minus. So this is minus up here, then minus x cubed. So minus and minus, there is still plus. So we have x raised to power 3. And then that goes on. So we can already see the pattern. It's x raised to power 0 plus x raised to power 1 plus x raised to power 2 plus x raised to power 3 plus x raised to power 4, and so on and so forth. So we can boldly say that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus all that. And of course, the reverse is also possible. So this is a very typical geometric progression, right? So I think I did this previously. So you have the first term to be a. I mean, the first term is a is 1. The common ratio is x over 1 or x squared over x, and that is simply x. So if you want to take sum to infinity is a over 1 minus r. So our a here is 1, then 1 minus r. Our r here is x. So you see, we get this back. Where we are coming from, we get it back. So this is just by the way. So that is a geometric series. So again, geometric series is 1 over 1 minus x equals 1 plus x squared plus x cubed plus all that. Okay. Now let's take an example in line with that. Approximate 1 over 0.8 using 4 terms. That means we're using 1, 2, 3, 4. We're using all this. So if we do that, first of all, you need to relate it with this. So it means here that 1 minus x is the same thing as 0.8. So you have 1 minus x equals 0.8. So you have to get the x because that's really important. So that implies that you have 1 minus 0.8 to be equal to x. That's if we transfer the x to the other side. So that means that x is equal to 1 over 0.8. 1 minus 0.8 is 0.2. So it means your x is 0.2. So it means that we're actually trying to evaluate 1 over 1 minus 0.2. That means anywhere you see x, you put 2. So this is approximately, so since we are using 4 terms, so the first term is 1, the second term is x, so we have 0.2. The third term is 0.2 raised to power 2. The fourth term is 0.2 raised to power 3. That's the approximated value. And the answer here is 1.248. Normally, what is 1 over 0.8? That's the question. 1 over 0.8 is like 10 over 8. 10 over 8. If you multiply both sides by 10, that's 10 over 8. And that's 5 over 4. And that is 1.25 or something like that. So we can check that out. Yeah, let's check that out in Desmos. 1 divided by 0.8. I think it's simply 1.25 or so. So 1 divided by 0.8. Yeah, it's 1.25. But then because of the approximation now, we got 1.248. And it is pretty close, So that's simply 1 plus 0.2 plus 0.2, okay, plus 0.2 squared. So you can see it getting closer, plus 0.2 cube. That's 1.248. So you can go plus 0.2 raised to power 4, getting closer, and so on and so forth. So we can keep going. The more terms you have, the more accurate your results. Okay, so that is for but geometric series. So let's take the last one. Which is binomial series. Interestingly, it's the same kind of idea applied here. So you can do the same for that, except that now, yeah, it's exactly the same thing you can do here. So yeah, you see a close relationship between the things we talk about, because at the end of the day, all knowledge converges to a point. So everything comes together: political science, philosophy, geography, physics, everything seems to converge at the end of the day at some point. So you have the binomial series, which is 1 plus x raised power alpha. So what that expansion I did for geometric series earlier is related to these two. So I'm just going to give you the terms and walk away to save time. So we have 1 plus x raised power alpha. So you can just do the same expansion I did the other time. So that'll just be 1 raised power alpha plus 1 raised power alpha x raised power 0 divided by 0 factorial, and then you keep going. At the end of the day, when you tidy things up, you get 1 plus alpha x plus alpha into alpha minus 1 all over 2 factorial, of course, multiplied by x squared, then plus alpha into alpha minus 1 into alpha minus 2 all over 3 factorial x raised power 3. So exactly the same process I described earlier. And all of this is for absolute value of x less than 1. The other one, I think it also has, this expression also, this one also has a condition that it is given for absolute value of x less than 1. So don't forget that condition is really important. So it only holds for absolute value of x less than 1. So in this case now, okay, we have that expression already. So if you want to take an example and you say that for square root of 1 plus x, for square root of 1 plus x, and then you take, okay, I mean square root of 1 plus x, right? Okay, let me just say that generally. So for square root of 1 plus x, you can really express this as 1 plus x raised to power half. That means that simply implies that your alpha, the alpha you're dealing with here, is half. So here alpha is 1 over 2 based on the expression. So it means if you want to evaluate this now, you have square root of 1 plus x, and you want to use okay, if we use all the 4 terms, right? So using all 4 terms, so alpha is half. So you have square root of 1 plus x, right? Is approximately 1 plus alpha is half. So you have half x plus, okay, not plus now, just put the half. So you have, okay, well, let's even say plus, right? So you have half. So alpha is half up there, and you have half minus 1, this here, all over 2 factorial. Then you have x squared plus, again, you have half into half minus 1 into half minus 2. You have x cubed all over 3 factorial, and all of that continues. So we can get a term for that. So this is approximately 1 plus half x plus half into half minus 1 is minus half, as you know. Then this 2 factorial is actually, we can write it as, since it is down there, we can write it as 1 over 2 factorial like this, then x squared. So everything can be on the same line, plus 1 over 2. Half minus 1 is actually minus 1 over 2. Then half minus 2, that is half minus 2 is minus 3 over 2, I believe. Yeah. Minus. So it's like minus 1.5. So that's minus 3 over 2. And then this 3 factorial can come as 1 over 3 factorial. So we can have it that tidy. Then x3 and all the rest continues. So we are still tidying things up. So we have 1 plus half x. Then, of course, plus 1 over 2 minus 1 over 2. Then 1 over 2 factorial is 2 also. So you have x squared here plus 1 over 2 minus 1 over 2 minus 3 over 2. Then this is 3 factorial, don't forget. So we have 1 over 3 factorial, that's 1 over 6 x cubed plus all the other terms. Okay, so that we have approximately still 1 plus half x, then minus 1 over 8 x squared, because 2 times 2 times 2, 8 x squared. Then here, this is 6 now. 3 cancels here, 1. 3 here is 2. So we have, this is plus and minus. So this, you have minus and minus plus. So everything is plus there. So that's minus 1 over, of course, don't forget this is 2. So that's 1 over 16 x cubed plus all that. So that is binomial series, and all the terms continue. So you can see most of the time power series have patterns. So we can actually write this as a pattern. So it means that if I want to go to the next line, that'll be okay. This is plus minus my okay, yeah, this is plus now. This is actually plus. Yeah, it's positive because minus and minus is plus. So it means the next one is going to be minus 1 over 32 x raised to power 4. You know, that's the pattern. So if it means that if you approximate, if you now approximate, root 1 plus 0.1. So it means you're approximating. So it means that x9 is your 0.1. In fact, I could actually write it as, approximate root 1.1. Okay. So it's left to you to know, to check that, okay, if you compare root 1 plus x, which is similar to root 1.1, it will simply imply that 1 plus x is equal to 1.1, which would mean that x is equal to 1.1 minus 1, and then x is equal to 0.1. So in case it's given like that, so you can sort that out. So you can now say, therefore, root 1.1 is equal to root 1 plus 0.1. So you can now use the expansion. You know, if you use the expansion and put 0.1 everywhere, so you have 1 plus 1 over 2 minus 1 over 8 into 0.1 squared, okay, plus 1 over 16, 0.1 raised to power 3, like that. And, you know, of course, it's approximation here, don't forget. So that's approximately 1.04875, okay? So we can check that on Desmos to see what the actual, okay, the actual thing should be like 1.0488, which you can confirm ourselves. So we have roots 1.1. So that's square roots of 1.1. That's 1.0488. But now when we are approximating, we have 1 plus 1 divided by 2 into 0.1, then minus 1 divided by 8 into 0.1 squared, okay? Then, so you can see it's getting closer. That's 1.04875. Oh, that's even 3 times. So if we continue, we add the next term, that's plus 1 divided by 16, then 0.1 raised to power 3. So even closer. And that's how it all goes. So that's so you can see it's really interesting once you understand what's happening. So this is really cool. Thank you so much for hanging out with me up to this point. If you have not subscribed to this channel, you don't want to miss other videos, so be sure to subscribe, and of course hit the notification bell so you can always get alerted when a new video is released. And of course, don't forget to comment, like, and share. See you next time. Bye.